One final example of being able to utilize the hypothesis test of two means. This time we're going to shift to the unknown and unequal standard deviation. So this is going to be a little bit different when it comes to being able to find degrees of freedom as well as the test value. All other steps are going to be the same. So in step number 2, when we generally compute the test or the t-critical value, the first thing we're going to have to do is we're going to have to use a new formula to be able to generate the degrees of freedom. After we find that, we can still create the distribution as we did before. So step 3 is going to be the same when we construct the graph. However, step 4, when we go through and try to compute the test value, is going to be slightly different. So there's two main differences: degrees of freedom and then computing the test value. All right, the test value is different because we have a different formula to be able to find the test value because of the estimator or the standard deviation has a different formula. A little bit easier to find the test value, more difficult to find the degrees of freedom. When we get to this step, I'll state how to go through and to put this into the calculator into steps. So let's look at an example of this. So we have a study of 18 randomly selected 12-year-old females produced a mean height of 59 inches with a standard deviation of 3.5 inches. A study of 11 randomly selected 13-year-old females produced a mean height of 61.7 inches and a standard deviation of 4.1 inches. One of the most important parts of the problem: the two populations are normally distributed and the standard deviations are unknown and unequal. So that's how we know that we're using these formulas. Remember, the first time it said unknown and equal, this time it says unknown and unequal. Is there significant evidence to suggest that the average height of all 12-year-old females is different than the average height of 13-year-old females? Test this at the 10% significance level. Alright, so as we did before, the null hypothesis, we would assume that if nothing goes on between the ages of 12 and 13 in females, that the average heights would be approximately the same, no significant difference. The alternative hypothesis says that, or asks us to be able to find a difference. So x bar 1 is not equal to x bar 2. And anytime we have a not equal, we have to define the two groups. So let's define group 1 as the 12-year-old females, and let's define group 2 as the 13-year-old females. We're going to collect some variables. So we have our 12-year-olds and we have our 13-year-olds. We're going to collect almost all of the same. So x bar 1, s1, and n1 to start. Now the average height of the 12-year-old females is 59 inches. The standard deviation is 3.5 inches, and the number of observations was 18. In the 13-year-olds, x bar 2 in this case is going to be 61.7. S sub 2 is going to be equal to 4.1. And the number of observations in group 2 is going to be 11. It also tells us that the alpha is 10%, and we know that it's a two-tailed test. So alpha is 0.10. However, because it's a two-tailed test, we need alpha over 2, which is going to be 0.05, and that's what we're going to look up once we get the degrees of freedom. Now we do have a fairly cumbersome formula for degrees of freedom. So I'm going to copy this. So we have it. And we're just going to substitute the values in directly to find the degrees of freedom. Okay, so it's a little bit taxing, but hopefully it won't be too bad. So when we substitute, we know that S1 is going to be 3.5, so it's going to be 3.5 squared divided by N1, which is 18, plus 4.1 square divided by 11, and all of that's going to be squared. We're going to divide that by 3.5 squared divided by 18. We're going to square that, and then we're going to divide that by 18 minus 1, which is 17, plus 4.1 square divided by 11. We're going to square that quantity, and then we're going to divide by 10. Now, the way to try to compute this is to be able to put the numerator first in your calculator and then the denominator secondly, into your calculator. So in your calculator, and I'm just going to define this as our numerator. In your calculator, you're going to say quantity 3.5 square divide 18 plus 4.1 square divide 11, and we're going to square that. So I'm going to type that in my calculator, and that's going to be our numerator. So just give me 1 second while I type it in. And if you want to type it in at the same time, just to make sure you get the same answer, I ended up with 4.879 for my numerator. For the denominator, we're going to type it in exactly as it looks. So for our denominator, that's going to be 3.5 square divided by 18. We're going to square that. We're going to divide by 17. To that, we're going to add quantity 4.1 square divide 11. And we're going to square that amount. And then we're going to divide that by 10. So again, I'm going to type that into my calculator. And again, make sure you're typing this in as well, just to verify. And I got 0.261. Finally, to get the degrees of freedom, you just divide those two values. So your degrees of freedom is going to be 4.879. And we're going to divide that by 0.261. And so we're going to get 4.879 divided by 0.261. And I get 18.69. And just like with degrees of freedom, remember that we always round down. Okay, so if we round that down, the degrees of freedom in this problem are going to be 18. So finally, we can find T critical. T critical is going to be found by alpha over 2, which was 0.05, degrees of freedom, which is 18, and we look that up in our chart. And I did not have my chart prepared. I apologize. So, one moment. And at 5% with 18 degrees of freedom, I got 1.734. All right. Even though that's taxing, the rest of the problem isn't too bad. Right? So now we're going to go ahead, we're going to construct the distribution. Remember, our distribution is a two-tailed test. Okay. So our right tail, we have positive T critical, which is 1.734. The left tail is negative 1.734 for the cutoff. Range of values, same thing as the other, as when they're unknown and equal deviations, negative to positive infinity, and directly in the middle of the graph is 0. Now we're going to compute the test value, and there's two formulas for the test value. So our first one is this animal right here, and then we also have the test value, so I'm going to copy both of these, so that way we can just copy them down and we can see how they work. So if we copy these, so first we're going to find this s sub x bar 1 minus x bar 2. So that's going to be equal to the square root of s sub 1 square, which was 3.5 square, divided by n1, which was 18. plus S sub 2 square, so that's 4.1 square, and then we're going to divide that by 11. Let me scroll up really quickly just to make sure I copy those correctly. 3.5, 18, 4.1, 11. Yep. When we put this into the calculator, we're just going to type it in as square root 3.5 square over 18 plus 4.1 square over 11. And we're going to go ahead and approximate that. And I end up with 1.486. And that's our standard deviation. And now we're going to compute the test value. The test value takes the differences of the means. So our test value t, remember our first mean was 59. The second mean was 61.9. And I'm going to go back up and verify that just to make sure. So we had 59 and 61.7. Excuse me. So we're going to get rid of that 9, turn it into a 7. And then we're going to divide by 1.486, which was the estimator of the standard deviation that we just got. Just like every test value, make sure you put in parentheses, and I'm going to compute this. And I end up with negative 1.817. We're going to go back up, we're going to plot that on the distribution, and it just barely falls into that reject region since negative 1.8 is a little bit less than negative 1.7. So really close. So our test value is negative 1.817. And that means we are going to reject the null hypothesis. All right, so we're going to go back up. I'm just going to copy this to make it really nice and easy. And at this point, we're probably really good about doing the conclusions. So we are going to say, since the test value falls in the reject region, we reject the null hypothesis. Hence, there is significant evidence. So we would say that there is significant evidence to suggest that the average height of 12-year-old females is different than the average height of the 13-year-old females. All right, so hopefully that makes sense to everybody. I would suggest going back through, making sure you can do the degrees of freedom formula as well as that estimator of the standard deviation formula.